let's go and get into the fun. I'm going to take you to show you what a Jamboard looks like, and then we're going to kind of play with it. So this is what a Jamboard looks like. If you have seen one of these before, great. If you haven't, it's not a big deal. It's very simple. If you look at it here, it's just like a sheet of paper. Can everybody see it? Steve, can you give me a thumbs up if you see the Jamboard? Good. And so here we can write. I know it's tricky, but we can use our mouse to write. Right? I can draw. Don't laugh at my drawings. I suck at drawing. I can erase with the eraser, right? So it's kind of a little scratch book, as it were, right? And I can do a lot of work here that I can share. I can do all kinds of stuff, okay? I can make my mouse look kind of fun, like this, to point at things. Oh, here is Keisha, fashionably late. Okay, and so let's go over very quickly some of these features, because you are going to be playing with this Jamboard pretty soon. Okay, so first, you notice there's a piece of paper here, what looks like a piece of paper, and there's a number, team number, and then there's next page. Look at how I'm navigating the pages at the top. Team 2, team 3, team 4, you get the picture, right? And so, and any of these pages are the same. You can manipulate this, which is a writing instrument. It's a pen, and you can change the pen the way it writes, if you like blue better or black better, if you want it to be a marker, if you want it to be a highlighter, if you want it to be a brush, if you're artistically inclined. So I like the pen, and for now I'm going to keep it blue, and so I can do stuff here. I can actually do mad stuff, right? So, and actually I'm doing now Control Z to undo, Control Z to undo. So, so the pen, the eraser, as you saw how it works, then these arrow, if you want to just move stuff around, to play with stuff, you use this arrow. Like I can now move these, yeah? So sometimes I would suggest come back to the arrow if you're not sure what you're doing, so you don't keep writing or erasing stuff when you don't want to. This is kind of cool. It's a sticky note. So we may use it today, and I will let you figure it out. So you can change the color of the sticky note and say, something, and you save it. And if you notice, it comes right here, right? You can move it around. This is the cool thing. As I'm showing you this, you, like when we share this live, everybody will be seeing it, okay? So I am doing these, I'm gonna delete this if I don't want it anymore. So take a look, I click on it, I click on these little 3 dots, and I delete it, and it's gone. So we're gonna do an exercise together, similar to what we do in class. We're gonna put you in random groups, in random pairs, and each pair, look at the team number, will have a team number, okay? So you're gonna work on this sheet with a partner. However, this is very important. This is very democratic, okay? Anybody can go into any page. Anybody can erase somebody else's work. I believe that you people are very smart and very mature, and you'll be kind with each other. We'll just work on whatever you have to work, okay? So I think it's gonna work. If somebody goes crazy and does stuff that it doesn't work for all of us, we'll stop the sharing and then we'll discontinue it. But I think it's kind of a cool opportunity for us to collaborate and feel as though we were in class. So as you move the pages, different teams, right? Okay, cool, very cool. And you can also, by the way, add an image. So let's pretend that today you have a question where you have to do a bit of math, and you do it on paper pencil, and you take a picture, and then you can upload it here. You can do it for your teammate, okay? So you can also do here, the only, of course, it has to be on your device. You can drag it, etc. Okay? And I think that's it. That's really the whole tour of the Jamboard. Okay. And so I'm going to go to the next bit. I'm going to pause the sharing for a moment. I need you to watch the video. The question will become very obvious in the video. And then I need you to take 4 or 5 minutes to work on your own on the question that is at the video. And then I want you to go to the Jamboard, right? And I want you to go to the page that you belong to. So if I was Andrew and Emma, I would go to team 10, yes? And so on and so forth. And then you can work together on the Jamboard to produce an answer, okay? So here's a link to the video, and then here's a link to the Jamboard. And I think that it's going to be great. I hope you found it fun. I was just having ridiculous fun watching you work and collaborate, almost as much fun as when we are in the classroom together. And so we'll talk about it later. And so here it is. We're going to go in random order. So we have here team 10, and team 10 is, well, Emma and Andrew. So one of you, can you walk us through these, please?
Okay, so we basically found out how long it would take each person to paint the house by themselves for an hour, and then we basically found a common denominator after adding an hour of each, and so it was 15 over 8, and then we just said that it was 1.9 hours.
Okay, so I like the way they explained this. They kind of, what they did was they made a unit of 1 hour to refer to the part of the job. So, and at the end you arrive at 1.875 or 1.9 hours. Let's see team 9. Team 9, who's Madiha and Malvi. You arrive at the same answer. Tell us a little bit about the process.
So I'm not sure exactly where my partner went, but our process was kind of the same. We were just looking for, we divided it into like how long it would take for them to complete it in 1 hour, and then we look for a common denominator and then just converted that into hours.
Okay, why do you use, when I see the sum is 8/15ths, but then you did 15/8? Why do you?
Yeah, Madiha did that, so I'm not really sure where she got that from. She kind of just like, I was trying to figure it out on my own on a piece of paper, and then like I look at the screen and it's all done. So I was like, okay.
Okay.
Yeah.
Okay. So then Madiha, I don't know if Madiha can.
I don't know if she
has access to a microphone. Okay. All right. Let's go team 8 quickly. Oh, nice. Look at this. I can move a little bit stuff around here. A random idea, and then here, there. Well, team 8, who is Stephen and Inalua, tell us what your thinking is, please.
So I was like, so I realized that.
Everybody else, if you don't mind, sorry, turn off your mics so we can only hear Inalua. Thank you.
Yeah, so like what a majority of everyone else did, I found the same thing with like, you can, Joe does like 1/3 of a house in an hour and Sam 1/5, so I added those up together. But the part that I didn't do was like the whole flipping thing, so I guess I got a different answer than everybody else. I came up with like, take them about half an hour to do the whole job instead from an hour and like 9 minutes, so it was a little bit different, I guess.
Stephen, anything to add?
I'm pretty sure I was one who was late to the race and didn't figure out what was happening until it was almost too late. But I would definitely started catching on after Inalua showed a common denominator, and just trying to compare apples to apples versus apples to oranges. Then you can marry them together and kind of, well, figure it out. But as I said, I think I was a little late to the race. So
okay, this is not a bad. I kind of don't dislike this equation. Okay. And then team 7, which is Malcolm and Kate. I know at some point Malcolm was desperately looking for Kate, and eventually they found each other, which is good. So either of you want to walk us a little bit through this?
So basically we just did the same thing as everyone else. So we did the lowest common denominator.
Mhm.
And then so we got to 5x plus 3x equals 15. So that's 8x equals 15, and then you just divide by 8 on both sides.
Oh, I like this
To find
equation here.
Yeah, so then x would be the time together it takes them.
Well, you did something a bit different, really. I think you did this equation, 5x plus 3x equals 15, right? So from this equation, I'm gonna highlight it. I think I have the power to highlight stuff. I feel all that. And so from here, I don't like that color. Sorry, I need a nicer highlighter color. Ugh, they're not very nice, are they? I'll try the yellow. So this equation here, I think that we hadn't quite seen. We saw a variation of it, but you did, by doing this equals 15, which is the lowest common denominator, that facilitated just going to here, and then x equals 15 over 8. Nice. So it's not, it's similar to the previous ones, but not identical. Cool. Let's see, team 6. Wow, look at this. And that's McKenna and Suzanne. I like the high five. So can you elaborate a little bit? If you can walk us through this very well worded solution.
Okay, we actually sort of worked independently and then compared our results. But we started off agreeing that it was going to take less than the 3 hours, because otherwise the fast painter, wouldn't want any help. And so we had a bit of an idea of what we were looking for. And then we both went in the same direction as everyone else, I think, that the fast painter could do 1/3 of the house in an hour, and the slower would do 1/5 in an hour, and together they'd get 8/15 of it done. And so if it was 2 full hours, that would be 16/15 of the house. So 2 hours was too much now. We knew our answer had to be less than 2. And then I think McKenna went in the direction that some of the previous boards went. I took it in a slightly different direction. We knew that 8/15 was done in 1 hour. We needed only 7/8 of that effort to finish the house, another 7/15 to finish it, so 7/8 of the previous effort. And so that gave us 1 7/8 of an hour, which would be 1 hour and 53 minutes.
And at the end, you ended up in the same place.
We ended up, yep. So
Cool.
Anyhow, so McKenna can explain hers then.
So,
There she
Suzanne
is.
pretty much explained it all already, but I kind of
No, I didn't.
approach previous slides, and then I just used the equation that was on the last slide to
Yeah, I
get
see
the
it.
15.
Yeah.
Nice. Well done. Well done. Okay, let's see here, team 5. Mark and Amish. Do you want to give us a quick little tour? I think there's a flow chart here happening. So either of you.
All right. Can you hear me?
Yep.
All right. So we realized that one person would take 3 hours. I don't.
Sorry.
Yeah, everybody else, if you don't mind, mute yourself. Except for Mark and Amish.
House, and they'd be both in the same level, I guess. And then we figured out that it would take less than 2 hours because we just because when they paint together they get 8/15 of a house done. So when you multiply that by 2, you get 16/15, which completes the house. So after that, we set the denominators equal to each other, and we made that multiply by x equals 1. And what we did was we divided by 1 by 8 over 15. That gave us 1.875. So that's how we figured out how long it would take to paint the house.
Okay, good. A bit. I mean, there's really a lot of commonality, right? And our team organization 101 is here, team 4, Karen and Zach. Okay, I gotta peep the competition. I think we're in first place. Oh, somebody was spying. I'm not gonna go into that. But all right. Okay. So would you friends like to give us a quick tour? Karen or Zach or both?
Yeah, so we kind of started off and we kind of like worked together the whole time. We never actually went on our own way. So I started off writing the like questions or whatever, and we figured out right away that it was 1/5 for basically what everyone was saying, 1/5 for the every hour for the guy that takes 5 hours, and 1/3 for the guy that takes 3 hours. And then I say common multiple, but I meant common denominator. And then she figured out that it was 1/3 plus 3/5. This is more her work, and which would add it up to 8/15. And the one house divided, this is the 2 green sides are hers, but one house divided by 8/15 equals 1.875. And then I actually did another side that I just rounded up to 1.9, but if you wanted to be more specific, you'd just do the 1.875.
Cool. Very cool. All right. So I think we are, everybody, I don't mean to take away any thunder from any team, but I think we kind of arrived here. If team 3, do you want to add something? Just let me know or let us know. No, I'm going to count from 3 down. And if not, I'm going to go to team 2. It looks very much what people are doing. And you guys took a while to be nice to each other. So and I think that was completely by accident. You deleted the team number and I was like, what's happening here? But eventually you figured it out. Good job. Team 2, again, same story. If Amber or Kirushka want to add something, if not, we're good. No, good. The 8/15 is here by the amount of the job. Here, I like this idea of the concept of the job, right? Which is the key idea here, that basically people are figuring out how long does each person do of the job. Go back to our plan. I'm going to actually take you to the homepage. Thank you. And you don't have to do this now, although I call it an exit ticket. But here, there's an assignment called shoveling the driveway, exit ticket. And you can find it by clicking here, and it will take you there, or in assignment, right? There's a question there that involves my buddy Braden and me shoveling a driveway. And so I don't want you to work, well, I mean, you can work on it now, but we're going to do a little bit of a review of something. So I think everybody kind of gets the idea of what's happening. Please, you pose your answer individually. And it helps me a lot when you do a JPEG or PDF files. So you can do the work, take a picture, upload your answer on to the assignment, right? So you can find it on the homepage. Let me just one more time show you. Here, shoveling the driveway, or you can also, I'm going to show you what you guys see as students under assignments here under rational functions, shoveling the driveway exit ticket. Okay, so that is for you to work on. And now we are going to go back to our next part, which was good job. So now we did the exit ticket. Now I want to just do a review of some key concepts on the reciprocal of linear functions, because even though many of you have done, have sort of completed the Desmos, I realized there were a lot of misconceptions. So I want to go over this, think about it as a kind of a mini lesson, but I want it to be, like always, a bit interactive. So I may be asking you questions along the way. I do need you to please, actually, let me see if I can expand my screen here. I don't know if I can. Oh, maybe, sort of. Let me see. Oh, I just made a discovery that I can find a way to see everybody here. Very good. I'm making me feel powerful. Okay, you guys are seeing the Desmo screen, right? Yes, thank you. Okay, good. So let's talk about these very quickly. I do need you to please, I cannot see the chat. I'm still not that good at that. But if, let's do these, Malcolm, I think you did an amazing job last time scanning the chat and letting me know if there's somebody who doesn't have a mic, wants to, has a question or a comment, okay? So think of the function that we're looking at. Let's begin here. Do you see y equals 1 over x plus b plus c? Okay. I know it's a bit different than the one in the assignment, but I want to talk about these in two ways. I want to illustrate what happens graphically, and at the same time, I want to make the connection of the algebraic representation. Okay, so come along, and I'm going to be asking you questions, and I need you to please answer. And I may be pointing at people just for organization sake, so that not everybody answers simultaneously. So please be prepared. And it's okay if I ask you and you're not sure to say, I'm not sure. Okay, no biggie. Okay, so let's just take a look at what happens. Let's imagine that C is 0, right, as it is now. So we have technically y equals 1 over x plus b. So this is the reciprocal of x plus b, and the slope would be 1 for the linear relation, right? And let's play with what happens when we change these parameter b. Well, I think you know by, let's just double check here for a moment. Take a look. I may b equals 1, b equals 2. I'm going to pause there for a moment. Can anybody tell me what happened? Actually, I shouldn't do that. I'm going to ask somebody in particular. So take a moment to think about it. We started at b equals 0, and now we made b equals 2, and this is how our graph changed. Ms. McKenna, would you tell us what happened?
So the B represents the vertical asymptote or the horizontal asymptote.
Okay, Namish, what do you think about that?
I think she had it right the first time. It was the vertical asymptote.
All right, all right. So let's take a look at it again. We're going to make it b equals 1, b equals, we're increasing b. And I want you to take a look at this purple line. This purple line is literally going vertical, right? Therefore, it is the vertical asymptote, like initially Amber mentioned, not Amber, but McKenna and then Amish confirmed, right? And the other point, the other observation is that when b is 6, the asymptote is negative 6, right? So think about it like this. If we look now, that's the graphic, right? We can see the graph. So imagine that b is 4, and remember that c is 0 for the moment. What would happen in this equation when I make b equals 4? Excuse me, when we make b equals 4, yes, actually we'll make b equals negative 4. When we make b equals negative 4, which is the opposite of this one, these become 0. And then our function is undefined, right? So our asymptote becomes the opposite value of b, right? And it's the vertical asymptote. Okay. Any comments about that? Malcolm, you're my scanner.
No, nothing.
No, give me thumbs up, people, as many of you as you can. I don't see a lot, but I'm going to assume that we're good because it's okay. So that's and of course, if b is negative here, now we would need to put a value here. If b is -5, if I put +5 in my equation, this becomes 1 divided by 0, who's undefined, and then I have c. So that b parameter determines my vertical asymptote. Okay, good. Now what about c? Let's take a look at what happens when we make c equals 2. All right, so I'm going to ask Mark to take a moment and look at what happened. And when you're ready, let us know what you think happened when we did this, when we went from c equals 0. In other words, our equation is 1 over x plus 0 to now 1 over x plus 2. What happened to our graph?
It changes the horizontal asymptote, but not backwards from. I don't know. Yeah, changes the horizontal asymptote.
That's right. It changes the horizontal asymptote, right? We can see these here. So these value, if you look at it in terms of a transformation, it's similar. It's really a transformation of the basic function y over x. Excuse me, 1 over x. So this c is changing my vertical asymptote. As c becomes 5, then the asymptote is 5, and if c is negative, the asymptote is negative. So algebraically, graphically, we can see it. I love these because it's easy for us to see. But what happens numerically when c equals 1 and b equals 0? What happens here? How do we figure algebraically what is the horizontal asymptote? Here is the key idea for this. We want to look at what we call the end behaviors. And that means, we talked about end behaviors before. What happens when we go x being very, very large all the way here, or x being very, very, very small? And we notice the value that the function gets close to as the x gets very big or x gets very small. And those end behaviors are going to give us what the horizontal asymptote becomes. Take a look here, right? So the equation of the vertical asymptote is x equals -b. If my equation is like this, right? The equation of the horizontal asymptote is y equals c. This is the movement that I have. So now when I change c, I can change both, of course. I can have these going up or down. So many of you in your equations, when we did in the Desmos, we're doing, say, 1 over x plus 3 or x minus 3, for example. And maybe that's partly because the exercise didn't take you there and you were unable to see the asymptote. And obviously, many times the screen just looked like this, right? And so you didn't know. And then when we make them look like this, these lines really do not exist in the function. These are, in a way, lines that we know are there, but they're not part of the function. So really, that's all I wanted to clarify, that take a look at how the equations connect algebraically, and graphically is very, very friendly to see what happens. So I don't know if anybody has any comments, anything to add.